Okay. So this is kind of a funky partial fraction decomposition because you only have an irreducible quadratic factor and it's a repeated irreducible quadratic factor, that x squared plus one, right? It can't be factored. So since it's repeated, you have to have the highest power of it and every lesser power down to. And then each of those irreducible quadratic factors, instead of just getting a constant, they get a linear constant, an ax plus b or a cx plus b or whatever. So this is how you would set it up. And now let's see how it's going to work out. So the next step is just to multiply both sides by the common denominator, which is actually going to be really not terrible. If we multiply everything by x squared plus 1 squared, we get the left-hand side being 2x cubed plus x squared plus 2x plus 2, and the right-hand side being ax plus b times x squared plus 1 plus cx plus d. Right? I know I didn't show my work here, but all I'm doing is multiplying both sides of this equation by my common denominator, which is x squared plus 1 squared. Pens are looking like trash today. I need to refill my pen supply here. So then if we multiply the right-hand side, and so I'll point out here, actually, before I keep going. Normally what I would do next is start picking convenient values of x. There aren't any here. That's actually not entirely true. If you really wanted to get pedantic about it, you can pick x equal to I, the imaginary root of -1. That's not easy for me to do in my head, so that's not what we should do. Although you could, if you pick I, you would get a 0 here, and then yeah, it would work, but it'd be just silly. So here we're just going to jump straight to equating coefficients. So if I multiply out the right-hand side, I get a times x cubed. I get a b times x squared. I get an ax times 1, and I get a b times 1 plus cx plus d. Yeah, this pen's gonna go too. I need to start actually throwing away pens that run out of ink instead of just like putting them off to the side. Keeping all the terms with the same powers of x together, I have a times x cubed. I have b times x squared. I have a plus c times x. And then I have b plus d. This is actually going to be really easy to find a, b, c, and d. A has got to equal 2. B has got to equal 1. A plus C has to equal 2. But since A is equal to 2, C is better equal to 0. And finally, B plus D has to equal 2. Which, since B is equal to 1, we're going to get D equal to 1 as well. So we could rewrite this integral on the next page. The integral of 2x cubed plus x squared plus 2x plus 2 over x squared plus 1 quantity squared dx is equal to our ax plus b, so 2x plus 1. Don't forget the integral, James. The integral of 2x plus 1 over x squared plus 1. And then our cx plus d is going to be 0x plus 1 over x squared plus 1 squared. And last time we were talking about partial fractions, I think I said pretty emphatically, for these irreducible quadratic factors, whenever you have multiple terms in the top, you have to break it up into that many fractions. So if you're getting two things at the top, you always break it up into two separate fractions. So immediately we'd write this as the integral of 2x over x squared plus 1 plus the integral of 1 over x squared plus 1 plus the integral of 1 over x squared plus 1 squared. Now, technically, the problem only said to rewrite it, but we're going to do it, obviously. So what I want to say here is that two of these integrals should be really, really, really straightforward. The first two. This one, I would like to imagine that all of you can just do that by doing the u sub in your head. U is the denominator, du is perfectly the top. The integral of du over u is the natural log of the absolute value of u. So this is going to end up being the natural log of the absolute value of x squared plus 1. You could actually even drop the absolute values here since x squared plus 1 is already always positive. But we leave it. Same deal here. This one should be an automatic you know. that the integral of 1 over x squared plus 1 is the arctangent of x. And now for this thing, which I was thinking about over the weekend, because I said last time how hard it was. It's not nearly as hard as I thought it was. I think I was imagining some other crazy integral. So let's actually do this one. So this integral, 1 over x plus 1 squared, is one of the few times you will do a trig substitution when you don't have a radical. Right? Usually we're doing a trig sub when you have like the square root of 1 minus x squared, or 1 plus x squared, or x squared minus 1, or some like 3/2 power, or something with a half a power. You technically don't have to have a square root. It's just usually that's when you end up doing a trig sub. So here, for this integral here, whatever that's going to be, so this 1 over x squared plus 1 squared. All right, which trig sub is it? Is it tangent, secant, or sine? It's got to be tangent because the plus sign looks like a T. So we know that x is going to equal tangent of theta, or dx is going to equal the derivative of tangent, which is secant squared theta times d theta. And then we just start replacing things. We rewrite our integral as 1 over, instead of x, we have tangent. So it's tangent squared theta plus 1 squared. Our dx is secant squared theta d theta. Every time we do a trig sub, what are we looking for? And that's a very vague and open-ended question. Specifically, we're looking for a trig identity. We're looking for something squared plus or minus something like something to turn into some other single trig function squared. In this case, the tangent squared plus 1 is equal to secant squared theta. So this is going to end up being the integral, let's put the secant squared on top, of secant squared theta over secant squared theta squared. Well, we have a secant squared on top and a secant to the 4th on the bottom. That reduces down to the integral of 1 over secant squared, which is a silly way to write that. We should really write that as the integral of cosine squared. And now we're in that situation where you have only even powers of sine and cosine, and you have to use that half angle formula for cosine squared, which is going to be 1/2 of 1 plus cosine of 2 theta. And instead of dividing it by 2, I really think writing the 1/2 out in front is the way to go there. We're finally at a place where we can anti-differentiate. We're going to get 1/2 times theta plus sine 2 theta divided by 2. And if you look back at what made us do this in the first place, x equal to tangent theta, what we're really saying there is tangent of theta is equal to x divided by 1. So we draw our little triangle. The opposite side is x, the adjacent side is 1 because tangent is the opposite divided by the adjacent, and the hypotenuse will be the square root of x squared plus 1. Sorry, it looks very small. But the sine of 2 theta here is problematic. We have to remember that sine of 2 theta is equal to 2 sine theta cosine theta. So this part here ends up becoming 1/2 theta plus 2 sine theta cosine theta divided by 2, or just sine theta cosine theta. Finally, we replace each theta with what is equal to, or each theta or trig function of theta, and we get 1/2 of our theta is just the arctangent of x, or the inverse tangent of x. Sine theta, looking at my triangle, is opposite of our hypotenuse, so it's x over the square root of x squared plus 1. Cosine theta is the adjacent over the hypotenuse, so it's 1 the square root of x squared plus 1. So putting all that back in here, we're adding 1/2 of arctangent of x plus, I'm going to simplify this as x times 1 on top over the square root of x squared plus 1 times the square root of x squared plus 1 is just x squared plus 1 plus c. So not still like the best thing you've ever seen, but certainly not as hard as I feel like I was implying it was. Not that terrible. Still, like, would I rather do other integrals? Definitely, but that was okay. So, just kind of one last reminder about the things we talked about last week. Partial fractions and trig substitution were on Thursday. And now we're going to move on to area, volume, all those kinds of things, all those kind of physical things. And I will say, one of the reasons some people do this section first is because a lot of the later kind of things we calculate, like arc length of a curve and surface area of a surface, some of the integrals are really gnarly and end up requiring trig substitution kind of right off the bat. So that is there's a good reason to have done this material before doing the other material. But there's also a perfectly good reason for doing it the other way first. So either way is kind of fine. Well, let's go ahead and start talking about area quickly, and then volume, and then all the other things. Let me make sure I'm in the right spot in my notes here. Yeah. So, yeah, let's do this one. So we want to find the area between, thank you so much, appreciate it. Why am I looking up there? Okay. Find the area between f of x equal to x squared minus 3x and g of x equal to x. And normally you wouldn't necessarily draw the region. I'm going to this time. So g of x equal to x is pretty straightforward to draw. It's just your usual line through the origin like that. And f of x equal to x squared minus 3x. If I was going to graph that, I know it's going to have an intercept, an x-intercept at 0 and at 3. So it's going to look something like this. So we're trying to find the area between these two curves. And the idea that's still going to kind of stick with us, and actually this idea is going to stick with us through talking about area or volume or arc length or surface area, is that we're going to take a representative strip or rectangle. Although I think I like the word strip better. So I'm looking at this rectangle here, and the area of that rectangle is equal to the height times the base. And in this case, the height is, well, whatever value the top function is minus whatever value the top bottom function is. So that's going to be, in this case, g of x minus f of x. And the base is some small change in x. You can write delta x. I prefer to write dx. And then if I want to find the total amount of area, we are going to add up all the rectangles. So the total area, which I didn't mean to pick that color pen. The total area is equal to the integral over, well, we'll find limits of integration in a second, of the function g of x minus f of x, which in this case is going to be x minus x squared minus 3x. So again, I'll just point out, there's your height, there's your base, and here we are adding up all the rectangles areas to get the total area. But we have to figure out what the limits of integration are. So it seems pretty easy to guess that the left-hand limit of integration is 0, because as far left as the rectangles, oh God, the words can come out of my mouth. As far left as the rectangles can go is 0. But the right-hand boundary is a little bit harder to just discover without using some algebra. So if we set these two equations equal to each other, we can solve for x. So I'm going to subtract x from both sides. X squared minus 4x equals 0. Factor out an x. X times x minus 4 equals 0. It looks like we're getting x equal to 0 and x equal to 4. So there's the integral that we're going to compute. Just as an aside here, if we hadn't drawn the region, one way you could tell which function's on top is to pick a point in between the two intervals, in between the two endpoints, and then plug it into each function to see which one has the larger value. So since we know that these intersect when x is 0 and x is 4, you could plug in x equal to 2 and then say that f of 2 is 4 minus 6, and g of 2 is 2. So clearly g is the bigger function. That's why we're doing g minus f, not f minus g. Or the other option is to not even care at all. And at the end of the process, if it comes out negative, put absolute values around every step. Totally valid. It is not my preferred way of doing it. I feel like it feels less nice, but it's very valid. It's always it's either the top function minus the bottom function, or if you actually do the bottom minus the top and you put absolute values, then you've got the area. So either way is fine. I like thinking about which function is the higher function, which one's the lower function. It's also a good idea when we start talking about like volumes of revolution. So it's good practice for future work. So calculating our area here, we're going to get the integral from 0 to 4. I'm going to simplify my integrand as negative x squared plus 4x. And then we're going to integrate. We're going to get negative x cubed over 3 plus 4x squared over 2, which is just 2x squared. From 0 to 4, plug in 4, we get negative 64 over 3 plus 2 times 16. Plug in 0, and we do get 0 plus 0. So we get something like, I don't know, 96 minus 64 over 3, which is 32 over 3. So that's how much area is between these two curves, is 32 thirds square units. And just in case it wasn't clear what I did there, I said 32 was 96 over 3, and then negative 64 plus 96 is 32 over 3. Questions, comments, thoughts? Okay, let's do a couple more. Let's see. Come ill prepared with pens, unfortunately. They're all dying. Actually, maybe try to throw them out. So let's look at the next situation. Yeah, good times. Find the area bounded. I'm sorry, find the area in the first quadrant bounded by the curves f of x equal to 8x, g of x equal to x squared, and y equal to 16. So we have to be a little extra careful here. But we'll just proceed as usual. So here's my f of x equal to 8x. It looks vaguely like this. I should say, I know I said before, like, we don't always have to graph it. If it's just two curves, totally fine. Just find the intersection points, top minus bottom. If it's some region that's bounded by more than two curves, graphing it's probably the best, easiest way to go. So I'm going to graph it. So I've got my, whoops, wow, okay, sure. My f of x equal to 8x. And then my g of x equal to 8 square x squared, something like this. Oh, they intersect somewhere up here. I should probably think about this point of intersection here. So if I set x squared equal to 8x, my solution is probably going to be x equal to 8 and x equal to 0. Yeah. Subtract 8x, factor. Yes. You get x equal to 8 and x equal to 0. So that point there is 8 comma 64. The reason I said I should probably look at that before I start graphing more is because if I'm graphing y equals 16, I should really know if that line is above or below the point of intersection. That's why I decided to graph it. And then, okay. And finally over here, here's y equal to 16. Yeah, I didn't really do a good job of this. So I feel like I even need more words to describe this region. So if I hadn't said in quadrant 1, we could be looking at maybe, say, this whole region here, bounded by my purple, my green, and my red function. In quadrant 1, though, there's technically two different regions we could be looking at. So I need to add another word. Bounded by the curves f of x equals 8x, g of x equals x squared, and above by y equals 16. So that means y equals 16 is the above boundary of my region. We're bounded above by that function. So we're looking at this region here. So you got some problems. The problem here that I would prefer to avoid is that if we use vertical strips like we did in the last one, we're gonna have to break this up into multiple integrals. Because at this point right here, which is where y equals 16, so x has to be 2, at the point 2 comma 16, there's a break or a change in which function is the top function. From 0 to 2, the top minus the bottom is going to be f of x minus g of x. But from 2 to, I think this point is 4, because if y is 16 and it's equal to x squared, that's 4 comma 16. From 2 to 4, the top function is 16 and the bottom function is still x squared. So if I was going to set up the integrals for this area, they'd be 2. The area would be equal to the integral from 0 to 2 of my top minus my bottom, which is going to be 8x minus x squared dx, plus then from 2 to 4, the new top function is 16. So it's 16 minus x squared. I've seen people kind of be sneaky on tests before and write this question as set up an integral for the area of this region. Don't find it, just set it up. And if this is your answer, it's technically wrong because I didn't set up a single integral, I used two integrals. It's kind of an asshole question, not to be like, it's not a nice question to ask because it's tricky on purpose. But the point of that question is you can set up the integral for this region using a single integral if we use a horizontal strip with and integrate with respect to y instead of a vertical strip. So that's what we're going to actually do. We're going to rewrite this as, in fact, we're going to draw the region again. I'm just going to draw the part of the region I want. So now for this region where the top function is y equals 16 and the right function is y equals x squared and the left function is y equals 8x. Now we're using a horizontal strip. And just like last time, the area of my strip is my base times my height. So the area of my strip, or my rectangle, whichever way I'm going to say it, my base now is the length of the rectangle. And the length of the rectangle is the right function minus the left function. And the height of my rectangle is a small change in which variable? If we're going up, down, it's a small change in y, meaning my height of a rectangle is a dy or a delta y, not a dx. So if you're using a horizontal rectangle as your strip, you know you're using dy or integrating with respect to y. If you're using a vertical rectangle, we know we're using dx. This idea is going to hold through future things, meaning volume, surface area, arc length. That's why we're talking about it now. So what that also means is I better not say that my right function is x squared and my left function is 8x because my variables aren't in terms of x, they're in terms of y. So I have to take each of these boundary equations and rewrite them solving for x as a function of y. So for y equals 8x, that's not too bad. Divide both sides by 8, and you get x equal to y divided by 8. For y equals x squared, again, not too terrible. We have to be a little bit extra careful here. We're going to solve for x. We're going to get x equal to, normally we would say it's plus or minus root y, but we only have one side of that. And we have the side where x is positive. So it's the positive root y, not the negative root y. So our right function is root y. Our left function is y divided by 8. And then our total area is going to be the integral from a low of y equals 0, that's how low my strip can go, to a high of y equals 16. And then it's y to the 1/2 minus 1/8 times y. And now we can integrate. I mean, I should say, we could have integrated here too. It's probably not that much worse to do it this way than to do it this way, but there is a natural's not the right word. There is a tendency for people teaching math to prefer that you write it in as few integrals as possible because it just feels like it's better. It might be better. I don't know. It doesn't really seem that bad, but much better to me. That said, if we do this, we're going to get y to the 3/2 divided by 3/2 minus y squared over 8 times 2, evaluated from 0 to 16. So we're going to get 2/3 times 16 to the 3/2 minus 16 squared over 16 minus 0. And we can simplify that. That's going to be, see, 16 to the 3/2 is 4 cubed, which is 64. So we're going to get 2/3 times 64 minus 16. So that's going to be 128 thirds minus 3 times 16 is 48 thirds. So we get 80 thirds. A lot of the time, people are going to care more about the setup than the actual execution here. So setting up, often on exams for this material, you'll see problems like setup and do not evaluate the integral for the area or volume or other things. But definitely, I should say, when you see problems like this on an exam, make sure you read the question carefully so that you're doing what is asked for, either setting up and then finding or just setting up. Don't be finding integrals if you're told not to find them. Yeah, let's look at, I have one more example here for this before we start talking about volume. Sorry, 1 second. There, I know I had another example in my brain, and it's I've got papers everywhere. That was hiding underneath other papers. There we go. Oh yeah, okay, let's look at that. So let's do one more. One more thing to be aware of with area specifically is an example like the following. Try and make this one not too terrible. So find, yes, thank you. I keep zooming in and then forgetting to zoom back out. But please keep telling me. Thank you. Find the area between f of x equal to x cubed and g of x equal to, sure, 2x. And we're going to do this one without graphing it first. So last time when we did the first one, we could have not graphed it by just finding the endpoints and then figuring out which function's higher on the interval. So we're going to do the same thing this time. We're going to find where these two functions cross each other. So we're going to set f of x equal to g of x. So we're going to get x cubed equal to 2x. We're going to be smart and bring everything to the same side. So I want that to be a 4x, not a 2x. Sorry, let's make our lives less terrible, right? That's what, yeah. Let me make sure here. 4, yes. Yes, sorry about that. Let's watch this 2 magically turn into a 4. Sorry about that. So if we set x cubed equal to 4x, and then bring everything to the same side, and then factor out an x, we can factor further as x times x minus 2 times x plus 2. So in this problem, there are 3 points of intersection, not just 2. So we get x equal to 0, x equal to 2, and x equal to -2. So that actually means we have to set up 2 separate integrals. The integral from -2 to 0 of the top function minus the bottom function, plus the integral from 0 to 2 of the top function minus the bottom function. And the reason we have to do that is because between this interval and this interval, the function that's on top actually changes. So between -2 and 0, well, if we plug in x equal to -1, f of -1 is -1 cubed, which is -1, and g of -1 is 4 times -1, which is -4. So in this interval, the top function is f, and the bottom function is g. But then if we look at the next interval, so between 0 and 2, let's set x equal to 1, we see that f of 1 is 1 cubed, which is 1, and g of 1 is 4 times 1, which is 4. And in this interval from 0 to 2, g is the larger or top function, and f is the bottom function. So the way we should actually set this up is that the area is equal to the integral from -2 to 0 of x cubed minus 4x dx plus the integral from 0 to 2 of 4x minus x cubed. Or, same comment I made before, if you didn't want to do all that work, you could just break it up as the integral from -2 to 0 and 0 to 2 and not worry about which way you're subtracting them and just put absolute values around each integral. Not my preference, but it is valid and correct. But I'm not going to do that. So then we integrate this, we get x to the 4th over 4 minus 4x squared over 2 from -2 to 0 plus 4x squared over 2 minus x to the 4th over 4 from 0 to 2. Plugging in, we're going to get 0 minus -2 to the 4th is 16. 4 minus 2 times -2 squared is 4. Plus, same thing over here. If I plug in 2, I get 2 times 4 minus 16 over 4 minus 0 minus 0. So I end up getting, let's see, that's 4 minus 8, so that's -4. And that's 8 minus 4, which is +4. So I end up getting 4 plus 4, which is 8. One thing about this example I'll point out, you might not have noticed it, but technically this example, the right area and the left area are just mirror images of each other because they're both odd functions. So this actually does look like this. Like here's one of the functions and here's the other function, where these two areas are just kind of reflections or rotations of each other, but that's not always true. So it's best to like always do this as, okay, if you have however many intersections you have that many -1 intervals. So if we have 2 intersections, 1 interval, like the first example. If you have 3 intersections, there's 2 separate intervals from the leftmost point to the middle and the middle point to the rightmost point. And you have to look at each of those separately and integrate them each separately and then make sure that they're both positive and then you add them together. Kind of fun. It's not, I mean, it's kind of. Yeah, I think that's the last thing I had to say about area. Unless you have any questions about area. No. Okay. There was one other thing I said, no, you're fine. Cool. Cool. No, that one's. Yeah, that's fine. All right. Oh, yeah. Sorry, I didn't see your hand. So the reason I did that was what I was really doing is I was avoiding graphing it. So if I look over here, if I plug in -1, I can see that the f of x function, which is the cubic function, gives me the point -1, -1, whereas the g of x function, which is 4x, gives you the point -1, -4. So I can see that between -2 and 0, the higher function is the one that has the larger y value of -1 as opposed to -4. So that's why I was picking a point in between -2 and 0 so that I could see which is the function was higher up or the top. And then similarly, between 0 and 2, I picked x equal to 1 to see which of these two functions was higher up. In this case, it was the straight line because on the curve I get 1, 1, and the line I get 1, 4.
Use those numbers to test out which is higher.
Exactly.
Which one doesn't count.
Exactly. Yes. Just like we could have done with our very first area example, where we had this, and if we hadn't drawn this picture at all, we could have said which one was on top by saying, oh, well, f of 2 is -2 and g of 2 is +2. So between 0 and 4, g is the higher up function or the top function. That's why we did the integral of g minus f instead of f minus g. Also, when you do this, if you end up getting a negative area, that means you probably subtracted in the wrong order. And so you should go back and check to make sure you know which one's the top, which one's the bottom. But I also point out, if you do that, an easy fix is just to literally, in every step, put absolute values around your whole thing so that you can just say, oh, it's positive, if you're sure that that's the mistake you made. So like if I, just to kind of show it, if I did this the wrong way, like sure, here's a good example. Let's say that we were trying to find, we'll do one more area problem just to point out how you can fix a problem. I'm going to find the area between the curves x equal to 4 minus y squared and x equal to 3y. Clearly, maybe not clearly, but to me it feels clear that since the functions have been written as functions of y, I'm probably going to be integrating with respect to y. So I'm going to find the point of intersection. So intersection points, I'm going to set 4 minus y squared equal to 3y. I'm going to bring everything to the right-hand side and get 0 equal to y squared plus 3y minus 4. That does factor as y plus 4 times y minus 1. So my limits of integration are going to be from y equals negative 4 to y equals positive 1. I will draw the picture afterwards, but I'm going to avoid that. So for now, I know I'm integrating from negative 4 to positive 1, and I'm going to incorrectly assume that my top function, although really if it's with respect to y, it's not your top, it's your rightmost function minus your leftmost function. I'm going to incorrectly assume that my top function is 3y and my bottom function is 4 minus y squared. So, okay, we're going to integrate. I'm going to distribute the minus sign first. Come on, James. So you get integral from negative 4 to 1 of 3y minus 4 plus y squared. I don't really care that things are out of order. I integrate. I get 3y squared over 2 minus 4y plus y cubed over 3, evaluated from negative 4 to 1. I plug in. So plugging in 1, you should not be showing any work, in my opinion. If I plug in 1, I know 1 to any power is 1. So when I plug in the 1 part, I'm just going to get 3 halves minus 4 plus 1/3. Minus, now when I plug in negative 4, I have to be careful. 3 times 16 over 2 minus 4 times minus 4 is plus 16, and negative 4 cubed is negative 64. 3. Okay, that's not the best. So here's something that's smart. No, it's not that smart, James. Could have been smart, but it's not that smart. Disappointing. Oh well. I was hoping something cool was gonna happen where I could put the thirds together and have it come out nice, but it doesn't come out nice. So let's simplify a bit here. Yeah, this is gross. I don't love the numbers here. I'm still gonna put those together. So I have, let's see, 3 halves minus 4. I'm ignoring the 1/3 for a second here. Minus 3 times 8 is 24, minus 16, and then 1/3 plus 64 thirds is 65 thirds. Okay, we're almost there. So let's see. That's a negative 44. So we have negative 44 plus 3 over 2 plus 65 over 3. I guess we need a common denominator. So that's going to be gross 6, negative 44 times 6 over 6 plus 3 over 2 times 3 over 3 is 9 over 6 plus 130 over 6. So that's going to be negative 264 plus 139 over 6, which finally, oh my gosh, it took way longer than I thought it was going to take, is going to give us negative 135 over 6. And we're like, I did all that work and it's negative. I really, really don't want to write it all again. right? So here's a quick save when you've made the error of subtracting the wrong way. It is totally valid to say, well, the absolute value of this actually is equal to the area. And then you have to put absolute values around every step. And then finally, my answer is positive 135 over 6, which I guess does reduce to 45 over 2. So that's what I was trying to make the point. Is you accidentally subtract in the wrong order, instead of writing all the work again in the right order, absolute values everywhere, and then say the answer is positive. As long as you're sure that's the mistake you made. Just to point out, if you were to draw this, here's what the region looks like. X equal to 4 minus y squared looks like a leftward opening parabola. And x equal to 3y, or y equal to 1/3 times x, looks like a straight line with a positive slope through the origin. And these points of intersection are the y coordinates. So there's your, well, if y is positive 1, x had better have been 3. And at this point, if y was negative 4, x had better have been negative 12. But if we were to draw a rectangle, oh yeah, it should have been the right function minus the left function, which should have been the 4 minus y squared minus the 3y, not the way we accidentally did it the wrong way. Cool. All right. Moving on to volumes. Oh yeah, question. I did not. Thank you so much. God, every time. Thank you. Thank you guys for asking. Please keep asking, because clearly I can't keep more than two thoughts in my head at the same time. So I always look at it and I'm like, okay, I'll pass this out in a minute, then get distracted. So cool. Let's talk about volume. Talk about keeping things in order here. Like, all right, yes. For volume, I'm going to put you somewhere. There you are. So volumes of solids. So there's kind of three different techniques for finding the volume of a solid. The first, so I'll say the three techniques are, well, two of them are by slices. So slices that are perpendicular to an axis. And then this is probably the one that everyone hates the most. I'll just say it straight up. Like we'll talk about this example first. And then the second type are going to be slices that are either disks or washers. These are typically called volumes of revolution, because you get it by revolving some area around an axis. And then thirdly are the shells, also a volume of revolution. Probably won't get to all of them today. So let's look at some of these slicey ones first. The phrasing of these is sometimes terrible. In fact, no, it's fine. Yeah. So, yeah, writing is always like the challenge. I know exactly what my brain is thinking of, but actually like making it sound nice is, so let's see. So let's say slices perpendicular to the x axis are squares whose base length is bounded by the parabola y equal to 9 minus x squared and the x-axis. I will say they're maybe written slightly more sensibly than I've written it, although not a lot. And I feel like reading this doesn't make it super duper clear what exactly is being described. So here's what's being described. Your region in 2 dimensions is this parabola bounded thing. So we're bounded by the parabola y equals 9 minus x squared and the x-axis. So something looking like this. So this is the region we're looking at in space. But then the idea is popping out of that 2-dimensional plane are squares popping like towards you. So if I draw this in a more flat way, so I'm actually going to kind of totally rotate it and draw it so that my y-axis is here, my x-axis is here, and here's my parabola, like that. Here are the squares I'm talking about. So the biggest square has its base right there, and it's going to look like that. And then if I move a little bit over, that square has a smaller base. Move a little bit further over, even a smaller base, until we get very close to the very end here. So the idea is we're trying to find the volume of that solid, where the base region in the XY plane is that parabolic thing, and then the shape is actually each slice that is, I said the wrong word. Sorry. Well, let me just fix this real quick. Slice is perpendicular to the y-axis. Sorry, not x-axis. My slices I meant to be perpendicular. So my slices are perpendicular to my y-axis, and they're popping up out as squares. Like that. Okay, so now we have to figure out how to set this up. Well, so what I'm really going to look at is I'm going to look at a little slice here, which is going to correspond to a slab of square. So I want to find the volume of that slab. Well, it's 3-dimensional. And for now, let's just call the base, I don't know, let's call it L. The height's L. And the thickness is the thickness of my vertical strip. Sorry, the thickness of my what strip? My horizontal strip, which is dy. So the volume of my slab is the length times the thickness. But dy tells me that I'm going to have to be integrating with respect to y. So I need to get this length in terms of y. So I essentially need the right function minus the left function. So the length is the right minus the left. Okay, well that means I have to do like x as a function of y. So my y equals 9 minus x squared, I have to solve for x here. So y equals 9 minus x squared equals 9 minus y, x equals plus or minus the square root of 9 minus y. The right-hand side is the plus, right? This right-hand boundary is x equal to plus the square root of 9 minus y. This left-hand boundary is x equal to minus the square root of 9 minus y. So then our total length is going to be the square root of 9 minus y minus the negative square root of 9 minus y, which simplifies nicely. It's just 2 times the square root of 9 minus y. So we're almost there. The volume of our slab is 2 times the square root of 9 minus y squared times dy. And now the only step left is to add up all the volumes of the slabs, meaning we're going to integrate. We're going to integrate from as low as our slabs can go, which is down at y equals 0, to as high as our slabs can grow, which is up here at y equal to 9. Right, because the top of that parabola is 0, 9. So my volume is going to equal the integral from 0 to 9 of 2 times the square root of 9 minus y squared dy. But this is not terrible, because 2 squared is 4, and the square root of 9 minus y squared is 9 minus y. So this is just going to be 4 times the integral from 0 to 9 of 9 minus y dy. And that's really not bad at all. So the nice thing about these like weird slicey problems is that usually the integral actually is relatively easy to anti-differentiate. Like it almost always ends up being some terrible square root thing that then nicely squares away. Not always, but like a lot of the time. So here, this is going to be, I don't think we need to finish this problem, but I'm going to anyway. 4 times 9y minus y squared over 2 from 0 to 9. You get 4 times 81 minus 81 over 2. Fun fact, when you take something and subtract half of it, you're left with half of it. So 81 minus 81 over 2 is 81 over 2. And you multiply it by 4, and you get 2 times 81, which is 162. That's the least important part of this problem. Okay. Yeah, let's do another one like this. These ones are always the funkiest ones, but they do come up occasionally. So we'll do one more, and then we'll move along to something else. Sure, let's do that. I'm not good at writing these questions the right way, so here's what I'm going to say. The region in the xy plane is bounded by y equal to the square root of x equal to 4, and y equal to 0. And slices perpendicular to the x-axis, I do actually mean the x-axis this time, are, how annoying do we want to be here? Sure, let's go with semicircles. That's not that annoying. I do think it's worth drawing these. I do think it's worth me drawing these just because they are hard to see the first few times you do them. I also point out your books have pictures of these things. So if you're looking for more pictures of these types of things, look in your book, right? The books are expensive. Someone paid money for them, probably you. So definitely use the thing you paid a lot of money for, because that book is not cheap. Look at the pictures in your book. They have nice pictures also. Yeah, especially because like this kind of thing is really not that easy to graph on Desmos 3D. Like it's not impossible, but it's hard. It's challenging to figure out how to graph it in Desmos 3D. So look in your book. There's good pictures. But here's what the graph's going to look like. So I'm going to draw two graphs. I'm going to draw the region in the xy plane, which is going to look like this. And that point is where x is 4 and y is 2. And then I'm going to, which I meant to do last time, I'm just thinking about really kind of tilting it back. So I'm taking the paper and just rotating it this way so that now, instead of seeing, the whole plane front on, it's looking like that. And then you're going to see what's popping up out of it. So if we tilt it back, not how you draw it, tilt it back, James. We tilt it back. What I meant to do was like this. And this is still my x-axis. This is my y-axis. Then my curve is just doing this kind of deal like that. And now popping up out of my curve are semicircles. So we're trying to find the volume of that shape. So again, I'm going to take a little strip here. Let's use green instead of red. A little strip here that's going to correspond to a slab here. A semicircular slab. So there's my semicircular slab. The width of that slab is dx. And well, I want to find the volume of the slab. So very broadly, the volume of my slab is the area of the slab times the thickness, which is dx. The area, well, is the area of a semicircle. And if I knew what the radius of my semicircle was, the area of that semicircle would be 1/2 pi r squared. Times dx. So now our job is to figure out what that radius is in terms of that function there. Well, it looks like the radius is just half of that function height. So my radius is 1/2 of the function, which is the square root of x. Okay. Yeah. Yeah. Seems right. Looks good to me. So that's what's going to go for my radius right there. So my volume of my slab is going to be 1/2 times pi times square root of x divided by 2 squared dx. And our volume, our total volume is going to equal the integral from as far left as 0 to as far right as 4 of 1/2 times pi times, let's simplify that as x over 4 dx. Again, not too terrible an actual integral, right? That's pi over 8 times the integral of x is x squared over 2 from 0 to 4. And plugging in, we get pi over 8 times 16 over 2 minus 0. So that's going to be pi over 8 times 8, which is pi. So that interesting looking solid has a volume of pi. And those are kind of the most reviled ones. That's maybe my own personal opinion. I hate these ones the most. The other volumes feel much more typical to me, and these ones are always like, what's going on? And often finding the equation for the area of the thing you've got can be not that nice. Sometimes it's a semicircle, sometimes it's a square, sometimes it's a triangle that's either equilateral or it's a right triangle that's isosceles whose hypotenuse is on the base. So it can get kind of gnarly. That's why we usually don't do too many of them. Okay, let's talk about the other things, which are much more interesting, in my opinion. Interesting, probably not the right word, but I like them better. What can I say? So, volumes of revolution. Yes, yes, of course. Yes, one of these days, maybe I'll know better, but not today. So, let's do the following. Let's find the volume. We'll actually use that same region of the region bounded by y equal to root x, y equal to 0, and x equal to 4, revolved around the x-axis of the, yeah, my phrasing here. I probably missed a few words. Find the volume of the solid for the region bounded by that revolved around the x-axis. Again, apologies for my phrasing. It's probably not standard, but it's enough. So I would say for these problems, for volumes of revolution, or for the other ones we just did, you always want to draw the region in the XY plane. You don't necessarily need to draw the 3D thing. I'm just trying to draw it to help you kind of make the connection there. But I don't think drawing the 3D thing is usually particularly useful or helpful on your own. Like it's not necessary. Something that's nice though. So we're going to draw the same region, looking like that. And so now the idea here is I'm thinking of, now for the first types of volumes of revolution, which is either using the disk method or the washer method, here's what I would encourage you to remember. They're really the same. One of them is just a simpler version of the other one. But more importantly, for the disk or washer method, the strip or rectangle that you're going to draw must be perpendicular to your axis of rotation. In contrast, for the shell method, which we'll learn about later, probably not today, your strip or your rectangle should be parallel to your axis of rotation. So what I always remember is shell rhymes with parallel. Perpendicular doesn't rhyme with anything. But so disk washer, perpendicular, shell, parallel. So since my axis of rotation is the x-axis, my strip better be vertical. On the other hand, if we were trying to do the shell method for this one around the x-axis, our strip would be horizontal, which we'll do later on when we learn it, just to kind of see how it's different. So if we're rotating this region around the x-axis, I'm really just thinking of what the strip is going to do when I rotate it around. And if we rotate that strip around, it's going to look like a disk. Okay, they're going, they just need to be stopping here. Okay, well, hopefully everything's all right up there. So we're going to find the volume of this disk. The volume of our disk, well, it's a circle times some thickness. So it's going to be area times thickness, which in this case is going to be pi times our radius squared, the area of a circle, times our thickness, which is a dx. Vertical strips always have a thickness of dx. Horizontal strips always have a thickness of dy if we're using usual x and y. But the radius is just how tall the strip is. It's just how far it is from the axis of rotation to the function. So in this case, our radius is equal to just the square root of x. So then if that's the volume of our disk, the total volume of our shape, which I'll just draw here, even though I think it's not really necessary, you can draw the shape by drawing your outer function and then reflecting it across the axis and then just trying to make it look 3D. Like that. So there's my shape, my solid. And here's my disk that got rotated around. My disk that got formed by rotating my strip. So the volume of this solid is going to be the integral from 0 to 4. We're just adding up the volumes of all the slices, of all the disks of pi times the square root of x squared dx. This again, not terrible at all. It's pi times the integral from 0 to 4 of x. That's just going to be pi times x squared over 2 from 0 to 4, which is going to be 8 times pi. So I would point out that we end up using the disk method when the region is flush with the axis of rotation. Or another way you could say that to yourself is when you draw a strip, no matter where you draw the vertical strip, it always touches the axis of rotation. Or another way to say that is the axis of rotation, in this case, the x-axis or the line y equals 0, is one of the boundaries of your region. We will now contrast that with something where that's not the case. So, yeah. Yeah, sure, we'll do that. So let's do this. Let's look now. Yeah, we'll do this classic one, sure. So now we want to find, get out of my way. What time have I got? Oh, okay. I got time. My clock is hard to see with that one. Find the volume of the solid generated by revolving the region bounded by, sure, y equal to x squared over 4 and y equal to, sure, x around, drum roll please, we'll start with the x-axis. So again, it's a good idea for any of these volumes of revolution to draw the picture. It does not have to be perfect, just trying to get a vague idea of what this region looks like. So I would point out that if we set these two things equal to each other, x equal to x squared over 4, multiply both sides by 4, 4x equals x squared, we're going to get x equal to 0 and x equal to 4 again. X squared minus 4x equals 0, so x equals 0 or 4. So those are going to be our limits of integration, probably. Let's draw it, though. So x squared over 4 is a parabola opening upwards. It's kind of scrunched down there. And y equals x, like that. So if I'm rotating around the x-axis, which way am I drawing my strip? Vertically or horizontally? Vertically, right? Because my strip needs to be perpendicular to my axis of rotation. My axis of rotation is horizontal, my strip has to be vertical. Notably, the strip does not touch the axis of rotation. I suppose there's one spot you could draw it in more dip, but it would have to, but to be flush, it has to do it wherever you draw the strip. So not flush, it's not going to be the disk method. It's going to be the more generalized version of the disk method, which is the washer method. So if we rotate this strip around the x-axis, here's what we get. We get a washer, right? That little rectangular bit just gets wheeled around the axis and comes back on itself, and you've got that washer shape. And the volume of this washer, instead of just being the area of a circle times the thickness, it's the area of the larger circle minus the area of the inner circle multiplied by the thickness. So we usually write it as area of the big circle minus the area of the little circle, all times the thickness. Where the distance from your closer function to the axis of rotation is your little radius, and the distance to your larger function or your further away function from the axis of rotation is your big radius. So in this case, the volume of our washer is, we also usually factor out the pi. Pi times my big radius squared, which is just x squared, minus my little radius squared, and my little radius is x squared over 4 squares. So that's the volume, or that's going to be the volume of our washer. And then the total volume here, again, we're just adding up all the volume. So it's going to be the integral from as far left as 0 to as far right as 4 of pi on the outside times x squared minus x to the 4th over 16 dx. Oh, there's stuff in the chat. Sorry, I didn't see the stuff in the chat. What's going on in the chat here? To answer the previous questions, someone asked if we could take the integral of f and the integral of g and subtract the results. And yes, that would totally work. We were doing the area way before. Yeah, you could totally take each integral and subtract the results. And then just a moment ago, why is the radius the square root of x, not the square root of x divided by 2? Like for this previous one? Yeah, so here, right, we're imagining rotating this whole thing around. So this circle, that's the radius. And that radius is just the height of your function. Or what I would really say, and it's actually a better way of saying it, the radius here is the difference between the function and the x or axis, which is y equals 0. So if you do root x minus 0, your radius is root x, not root x divided by 2. Unlike the previous problem where it was divided by 2 because we were taking half of that length as our radius. All right, so sure, we can finish this problem. It's going to be pi times x cubed over 3 minus x to the 5th over 16 from 0 to 4, and we get something. We get pi times 64 over 3 minus, let's be smart here, 4 to the 5th is 4 times 4 times 4 times 4 times 4 over 16. Cancel a couple of those, and you get, oh, haha, interesting, interesting, James. Yeah, what did I do? I did something. So why am I saying what did I do? Well, look at what my answer is. 4 times 4 times 4 is 16, 64. Is the answer positive or negative? It's definitely negative. 64 thirds minus 64, that's a problem. I didn't do this on purpose. I made a mistake somewhere, but this is a good check, right? I'm seeing that my answer is negative. I need to go back and look and see what I did wrong because I definitely made a mistake somewhere. So where did I make my mistake? You know what? I didn't check to see which function was actually bigger, but I'm pretty sure this one's definitely the bigger function. Between 0 and 4, if x is 1, y is 1. If x is 1, x squared over 4 is 1/4. That's the smaller one. That's the bigger one. Let's see my big rate. Let's see. Yeah. Interesting. There's my big radius. There's my small radius, x squared over 4 squared. I'm at a loss. What did I do wrong? I'm really like, I don't know. I made a mistake somewhere. I don't know what the mistake is, and it's unfortunate.
I think you integrated it wrong.
Okay. Oh, I did. What did I forget? Divided by 5 times 16. So, but again, it's good to think about what your integral means, right? If this integral represents a volume and we can see that we're getting a negative answer, we got to go back and look at something. Good catch. Thank you so much. I would have gone crazy. So it's not 64 over 3 minus 64. It's 64 over 3 minus 64 over 5. And then the smart play is to factor out the 64. And then you've got 1/3 minus 1/5, which is 5/15 minus 3/15, which is 2/15. So we get 64 times 2 pi over 15. Okay, let's do one more and then we'll call it a day. We're going to go around the y-axis this time. So same region, but now around the y-axis. So we'll draw the same picture, kind of. Here's the region we were rotating, but now we're going around the y-axis, meaning our strip shouldn't be vertical anymore. Our strip now needs to be horizontal. I should probably write down with you. This was still y equal to x squared over 4. This was y equal to x. So now our strip better be perpendicular to the axis of rotation. And when we rotate this around, we're again going to get a washer. And the volume of our washer, once again, is big circle area minus little circle area, all times the thickness. In this case, well, in fact, so in this case, we have to rewrite the functions, right? Y equals x squared over 4 becomes x squared equal to 4y becomes x equal to, it's on the positive side for x, so the positive square root of 4y, which I would make a change here and say the positive square root of 4y is 2 root y. That seems like the smart way to go. And y equals x is x equals y, so that's not a big deal. So here's my little radius, which is the closer function, so x equals y, and my bigger radius, which is going to be x equal to 2 root y. So the bigger radius is x equal to 2 root y. The smaller radius is x equal to y. So the volume of our washer is going to be pi times our big radius squared minus our little radius squared dy. And then our total volume is going to be the integral from, oh, this point here, we said that x was equal to 4. I guess y is also equal to 4 because it's on the line y equals x. So the limits of integration look the same. It's still from 0 to 4, but it's not x equals 0 to x equals 4. It's y equals 0 to y equals 4. We're thinking about how far down and how far up that horizontal strip can slide. And then our integral, we've got the pi on the outside. Inside, we're going to square. I guess you didn't really need to make the simplification since we're going to square it anyway. It's still not a bad idea, though. Squaring this, we get 4y minus y squared dy. We integrate, we get pi times, not making any mistakes this time, James. 4y squared over 2, which is 2y squared, minus y cubed over 3. Evaluated from 0 to 4. So we're going to get pi times 2 times 16 minus 64 over 3. Let's see, that's going to be, multiply this by 3 over 3, you get pi times 96 over 3 minus 64 over 3. So 32 pi over 3. And not that this should be surprising one way or the other, but rotating around one axis doesn't give you the same amount of volume as rotating around the other axis. So definitely different volumes every time, practically. All right, next time we'll talk more about the disc washer method and rotating around axes that aren't the x-axis or the y-axis and seeing what you have to do to change that, as well as talking about the shell method and maybe arc length.